Moisture and precipitation process. We've got 4 lectures, and we're going to begin with lecture number 1, humidity and the condensation process. And then we'll be moving on to specific ways in which precipitation is produced in the following lectures. So let's begin with the 3 states of water. Now, water is a unique substance in that it can exist in all 3 states at Earth's surface temperatures. So we're familiar with the liquid state, the solid state, and, well, the gaseous state. And we're going to start with the gaseous state, moisture in the air, humidity, and it's, water vapor. That's the term we're going to be using. Now, what we're going to be concerned with, all right, in terms of, all of these different phase changes, we're going to be concerned with just one, all right, condensation. What we want to learn is how we go from the gaseous state, moisture in the air, or water vapor, and then how we get it to actual water droplets to make clouds and precipitation. Let's define humidity now. Certainly we're familiar with humidity in Louisiana. Specifically, it's the amount of water vapor, or just simply moisture, in the air at different temperatures. And that's important. The word temperatures is very important because the amount of water vapor the air can hold is dependent on the temperature. Let's look at the relationship. And the relationship is this, that as temperatures increase, the air's capacity to hold water vapor also increases. And so we've got the temperature up here from very, very cold to very warm. And then on the vertical axis, it's the amount of water vapor in the air. Now we just measure it in grams per kilogram, but basically 0 grams, no water vapor to a lot. And here's the relationship. So it's very cold outside, and we're not holding that much. And then progressively, as it gets warmer and warmer and warmer, the air can hold more water vapor. So in general, we say that cold air, cold air and progressively colder has a small capacity to hold water vapor. And if you think about it, cold air contracts and, it can't hold much water vapor. And, and then we say in general, warm air and progressively warmer air has a large capacity, as you can see. And of course, water, warm air expands, and so you have a larger capacity to hold moisture. So let's talk about Louisiana. Now, we're famous for our humidity, and, our humidity levels are really high in summertime, and our temperatures usually in summer are somewhere in the 90s. So we, indeed have a large capacity because we're warm in summertime. And so in this graph where, they're showing, in the 90s, our capacity is usually somewhere around 35 grams, all right? But then again, you know what? Phoenix is much hotter in summertime. Much hotter, 110 degrees. And so the question is, even though Phoenix, a desert, has a larger capacity, why are we so humid and why are they a desert? Well, it's the Gulf of Mexico. You know that. So we've got a source of moisture to fill in our capacity. So we have evaporation of water from the Gulf of Mexico, and so we're filling in 10 grams, 20 grams, 30 grams, we're 35 grams. And so we're constantly, filled up or near or at capacity. That's why we're so humid, because we're, filled up to capacity. Now, Phoenix has the desert of Mexico to the south of it. And so it's rarely filled up. It doesn't have any water to evaporate. And so it's never anywhere near capacity, even though it has a huge one. And so that's why it's a desert. All right, let's look at the term saturation. This line, this green line here, represents saturation point for each temperature. So this saturation line represents the maximum amount of water vapor the air can hold at different temperatures. So we've just kind of alluded to that. Here, let's take a look at 26 grams. That's kind of representing maybe about 85 degrees. So at 85 degrees, the air can hold a maximum of 26 grams, a maximum. And so it can hold, 5, 10, 15, 20, 25, 26 is the maximum. That's it. It can't hold 27. It's impossible. 28, 29. It's impossible. All right. And so, yeah. So the air can hold, up to a maximum. Now, once you fill up the air to capacity, it's said to be saturated. You're just filled on up to capacity. Now, what happens is, all right, once you fill up to capacity, this is the point where condensation occurs, the phase change from water vapor that the air is holding to actual liquid droplets. That's just like the beginning point. Now, what you've got to do is you've got to add more water vapor from evaporation, but the air can't hold it. And so the water vapor pressure is increasing and increasing. And so literally you add more water vapor, and the water vapor pressure inside the air literally forces the phase change. And so, you add more water vapor, and the pressure inside the air, right, forces condensation. So the more evaporation you have, the more condensation, clouds, fog, dew, and ultimately precipitation. All right, let's talk a little bit more about that concept by using a term meteorologists use a lot on TV, and it's called relative humidity. And it's always shown as a percentage of relative humidity. Now, what I want to say is, what that percentage means. It shows you how close the air is to saturation. And let me give you the formula that is used. What you need to know is the actual amount of water vapor in the air, and then you need to know the saturated amount. And then you multiply it by 100 to get a percentage. Now, you've got to know the temperature. You've got to know the temperature so you can use this little formula, because the saturated amount is temperature dependent. So what I want to do is just take that 85-degree reading right here, all right? And so we can see the maximum amount of water vapor the air can hold at 85 degrees is 26 grams. Now, what we're going to pretend, right, at 85 degrees, the air, right, is holding 13 grams. So that's the actual amount, all right? And so you can actually see, you don't even need the formula. You can actually see that the air is holding half of what it possibly can. So let's just do the formula. And so the actual amount of water vapor is 13 grams in this example. And it could potentially hold 26 grams. And so we're holding half of what is needed in this example. And so the relative humidity is 50%. So are we anywhere near saturation? No, right? We're holding half of what is needed. So we still have to fill up the air with another 13 grams to get the air filled up and to have condensation begin. Let me just give you another example. Now, we're at the same temperature, right, at 85 degrees. And let's say, right, the actual amount of water vapor in the air is 26 grams. And we know, according to this figure, that the saturated amount is 26 grams. So you just do the division and just 1, multiply it by 100 to get a relative humidity of 100%. And so the air is saturated. And so 100% relative humidity means you're filled on up, right? And you're saturated. Saturation means 100% relative humidity. Right? And so if it's 98 or 99%, you're pretty close to saturation. But if you're at 10% or 20%, you've got a long way to go, right, to fill up that capacity. Now, there are 2 ways to reach saturation. And this is the first way is the way I've been talking about, evaporation from the oceans, to fill up, right, the capacity at whatever temperature it is. Right? But in actuality, it's a relatively slow process. It usually takes days, to evaporate from the oceans and, slowly increase the amount of humidity in the air. And, eventually, you can reach saturation, but it usually takes days. And you kind of notice that humidity sometimes is increasing more and more and more over a series of days. Now, the second way is the really important way, and that's by changing the temperature. And it's a really fast way. So this is the important way. This is the way this is what we're going to be talking about. All you need to do is change the temperature, and that is a very fast way to reach saturation. It takes hours. Now just think about it. Think about a typical day. We've already talked about, the daily low temperatures about sunrise, and then, by late afternoon, 3 or 4 o'clock, we reach our maximum temperature. So on a typical day around here, we have a temperature change of 20 or 30 or maybe even 40 degrees between the daily low and the daily high. And that temperature range is usually enough, right, to dramatically change the relative humidity. Now, specifically, this is probably the most important statement that I'm going to say for this entire section of 4 lectures on the moisture precipitation process. This is it. This is what you've got to get straight in your head. You lower the temperature and you increase the relative humidity. And that's what we're concerned with. We want to increase relative humidity to get to 100%, to have that phase change to condensation. All right, and so eventually we can, have fog or dew, or ultimately clouds is what we're really talking about, and get precipitation. So let me give you an example. What we're going to do is we're going to lower the temperature during a day. It's going to be kind of an extreme example, and on that day we're holding 5 grams of water vapor. And again, on any one day, the amount of water vapor doesn't really change that much. All right. So what we're going to do is we're going to start at 85 degrees. At 85 degrees. All right. And we're going to say that on this day, we're going to have a temperature decline from 85 to 30 degrees overnight. So that's kind of a dramatic example. But during this overnight period, this temperature drop, we're going to say that the air is holding a steady amount of 5 grams, which is quite common. That's what it does. And what we're going to do here, just to simplify it, we're just going to say, 25 grams, just so we can divide easier. So we've got the actual amount of water vapor in the air, 5 grams, and at 85 degrees, the saturated amount we're going to say is 25. And so you do the division, and it's 0.2, and you multiply by 100 to get 20% relative humidity. Now what we're going to do is we're going to lower the temperature overnight. Now, we're going to lower the temperature to 30 degrees. And now, all right, we're still holding our 5 grams, and so that's the actual amount. But now, because it's colder out, the air has a smaller capacity to hold water vapor. And so the saturated amount at 30 degrees is 5 grams. So we're now holding the maximum amount of water vapor. And so we've increased relative humidity to 100%. So it all has to do with the temperature. I mean, warm air has a large capacity, and then cold air progressively has a smaller capacity. And so you lower the temperature, having a smaller capacity, having the same amount of water vapor in the air, and chances are you're going to increase relative humidity. Well, chances are you're definitely going to do it. So you need to know that in order to understand the precipitation process. You've got to chill the air. All right. Okay, now the opposite is true, and we're not so concerned with this because we want to get to 100% relative humidity to get clouds and precipitation. But obviously, if you increase the temperature, you're going to lower relative humidity, right? Because warmer air has a larger capacity. Let me show you this figure from the book. And it's pretty much illustrating what I've just been trying to tell you. What we've got is, a little blue box here representing the amount of water vapor in the air during the day. And like I said, it's usually pretty constant. Not really changing that much, maybe a little bit, but here we're just going to show it constant. And we've got 4 times during the day, 41 degrees, and very early, in mid-morning, 61 degrees, and by mid-afternoon it's pretty hot, all right? And so At 4 in the morning, we've got the cold air can't hold much moisture, so we're usually at or near capacity. So normally, it'd be 80 or 90, or in this case, 100% relative humidity. Now, as we warm up, warm air has a larger capacity, and so here in the mid-morning, I mean, in this example, we're holding 50%, and so we're warming the air, and we're decreasing relative humidity. And now we're getting really, really hot out, all right? And we've got a large capacity when it's 90 degrees, but we're still holding that same amount of water vapor. And so now we're only holding 20% relative humidity in this example. So we've got an inverse relationship that you need to know. Now, typically in the morning, when we have our lowest temperatures of the day and our smallest capacity, we're going to have our highest relative humidity, right? And then in the afternoon, when we have our highest temperatures of the day, because we have a large capacity, we're going to have our lowest relative humidity. Now, in Louisiana, let me just say, 20% is not that common, right? Maybe, in wintertime, we might get a really cold, dry Arctic air mass, behind a super cold front, and we might get down to 20%. In a year, but it's not very, very common. Normally, in the morning around here, we're usually in the 70s, 80s, 90s, and 100, right? And then in the afternoon, I mean, maybe in wintertime, we're in the 40s and 50s. Typically in summertime, we're usually in the 60s or maybe even 70. But these are like average annual morning and afternoon relative humidities for Louisiana. So these are pretty high numbers. All right, I've got another term. It's called dew point. And we abbreviate it DP. It is the temperature in the atmosphere where saturation occurs. The temperature in the atmosphere. So it's a temperature. We call it dew point temperature. And of course, saturation means you've reached 100% relative humidity, either by filling the air by evaporation, or more importantly by cooling the air. And this is what I want to show you. Now, you don't understand dew point now, but I'm going to show you an example of cooling the air. All right. Yeah. All right. What we're going to do is imagine a hot, steamy summer day in South Louisiana, and we're going to be in Thibodaux. We've got Nichols campus here. And and so we've got a built-up area, right? This is what I want to try to. They've got buildings here, and then there's parking lots and asphalt and rooftops, and so so usually built-up areas are usually much hotter than the surrounding area. And so I'm just putting like sugarcane or marsh or swamp or forest, compared to the natural environment. And so what we're going to wind up doing is superheating an area compared to the surrounding, natural environment. And what's going to wind up happening is, so we've got a superheated area on the ground, and that's going to heat up the atmosphere just above it. And literally, all right, we've got some terms here. This superheated area is called a hot spot compared to the surrounding area. That's the terminology in meteorology. All right, and then what's going to wind up happening is we're going to actually create a bubble of heated air, a bubble or a parcel of heated air. And this hot spot, a warm air, as we know, is going to rise. This heated bubble of air is going to rise. And as it's rising, it's called a thermal. Thermals are rising hot spots, right? Rising parcels of air. And I mean, if you've ever been in an airplane on a hot summer day, I mean, you get turbulence and bumpy and bumpy and bumpy, particularly if you're going through clouds. And that's those hot spots, these thermals rising. Even like soaring birds, they kind of are soaring, and they're catching one thermal after another. They don't need to flap their wings. They're just kind of catching all these thermals rising that are, keeping them flying. All right, now the important thing is that this heated bubble of air is going to rise and it's going to cool. Now remember, as we're rising in the troposphere, what is going on to temperature? Temperatures decline in the troposphere. You remember that. right? It gets, very, very cold by the time you're about 9 miles up. It's 60 or 80 below zero, all right? And, it's maybe whatever temperature it is at the ground, 70, 80, 90, whatever. So what's going to wind up happening is as this hotspot rises, this thermal rises, temperatures are going to cool. Temperatures are going to cool. Now remember the most important statement that we just learned. You lower the temperature, you cool the air. What happens to relative humidity? It increases because cold air has a small capacity. So a typical relative humidity in a hot, steamy summer day in South Louisiana, right, in the afternoon, it's not 20%, right? It's usually something like 65% would be a pretty common afternoon relative humidity on a hot, steamy summer day. And so what's going to wind up happening is as this bubble of air, with 65% relative humidity and it's in the 90s, it's going to rise and it's going to cool, right, to 80s and whatever. And what's going to happen to the relative humidity, as it's rising and cooling, the relative humidity is going to increase inside this bubble of air as it cools. So what once was, right, a bubble of air with 65% relative humidity at 90-some degrees, we've cooled it to 80, whatever, and usually in the 70s is pretty much our dew point temperature, meaning that we've chilled the air and increased the relative humidity finally to 100%. So that's the definition of dew point. It's the temperature in the atmosphere where we reach 100% relative humidity. And usually our dew point temperature around here is in the 70s in summertime. And you usually reach it at a couple thousand feet, 2,000 or 3,000, maybe even 1,000. So what's going to wind up happening is now we've reached saturation. And what's going to wind up happening, condensation is going to start to occur. And typically what's going to happen is we're going to have a flat cloud base representing that dew point temperature. So all of the bubble of air is rising, and immediately it's reached saturation, and we're going to start condensation. Now, when we condense water vapor, what you wind up with is not a giant raindrop. You wind up with the technical term tiny water droplets. These are like tiny little pinpricks, right, of liquid water. I mean, they're so tiny. They defy gravity. They can actually remain suspended in the atmosphere, defying gravity. That's how tiny they are. Now the question is, do all clouds produce precipitation? No. In order to produce precipitation, what you need is time for the cloud to grow. Here we go. And I can't really throw my cloud here, but you've seen the clouds. Imagine looking at a cloud in summertime, and you can just see them growing and billowing up, thousands and thousands of feet. And as these clouds are growing, what's happening is these rising thermals, and they're still rising and cooling and condensing. As they're rising, these tiny water droplets are starting to coalesce. They start to bump into one another and join and get larger and larger and larger. And as you move thousands and thousands and thousands of feet in the growing cloud, there's a certain point where these tiny water droplets have grown large enough by the process of coalescence or joining that the raindrops now are big enough and heavy enough that that gravity now can pull them back to earth and fall as raindrops. So this is a nice little diagram kind of illustrating the concept of a heated bubble of air, right, over a hot spot. And so we've got a hot spot here, a bubble of air or parcel of air, and warm air now is going to start to rise. Warm air becomes less dense and rises. And so here we've got a thermal rising. Inside this bubble of air, it's getting cooler and relative humidity is increasing. And, like I said, our typical relative humidity in summer is somewhere around 65%. So it's rising, right, and cooling, and relative humidity is increasing. And so there's a certain point where it's increased to 100% relative humidity. And so we've got a temperature here that represents, dew point temperature. And we've now started to make a cloud. So, even though it's 65% or whatever the relative humidity is at the ground, if you're looking up at a cloud, what is the relative humidity up in that cloud? It's got to be 100%. It's got to be 100%. Yeah, so it's typical to see clouds, in the sky to have kind of flat cloud bases, and that's representing the dew point temperature. Right. So as you know, it's 90 degrees at the ground, and then as you move up, there's a line of 80 degrees and 70 and 60 and 50. And so whatever the dew point temperature is, it's going to represent kind of a line or at a certain altitude, and you're going to wind up with flat cloud bases. So that's a really, really common thing. So you can tell the dew point temperature, whatever it is. And even flying in an airplane, you see all the clouds forming at the exact same elevation. Now, I just kind of want to move on and talk about another kind of cloud formed. But this cloud is forming at the ground, not at 2,000 or 3,000 feet by cooling the air. And I want to talk about fog. And fog is nothing more than a cloud that is formed at the Earth's surface. And so what we've got to do, instead of getting the warm air to rise and cool to dew point, what you've got to do is you've got to cool the air at the ground surface instead of getting that bubble of air to rise and cool and make a cloud at 2,000 or 3,000 feet. And so there are certain ways that you chill the air at ground level a few extra degrees to actually form a cloud at ground level, and you've reached dew point at ground level. And there's two ways to cool the air at ground level and make fog. And so there are two types of fog. The first type is called radiation fog, and it occurs when we have excessive loss of long-wave radiation overnight. And it's got to be clear outside. Now, remember, long-wave radiation is the heat given off by the Earth all night long. And you're going to excessively chill the Earth's surface on a clear night. Now, remember, if it's cloudy, clouds act like a blanket, and it's going to keep the lower atmosphere warm. So what you need is clear overnight conditions to chill the air, the few extra degrees. Now, it's got to be calm outside. It can't be windy for condensation to occur. And you do need some moisture in the air, pretty high relative humidity. So you cool the air those few extra degrees with the excessive loss of long-wave radiation, and it'll bump that relative humidity up to 100%. So you do need moisture, some sort of moisture in the air. So instead of being 90% relative humidity, you'll chill the air and you'll be able to get it to 100% relative humidity. This is kind of a neat picture here of radiation fog. And what it is, it's a cloud at the ground. Now, radiation fog is the most common type of fog. When we have fog in the mornings, it's radiation fog, for sure. Now, there is another kind of fog known as advection fog. Now, this is very common along the west coast of the United States. Now, advection means horizontal movement of air. Horizontal movement of air. And so, by definition, advection fog occurs when you've got warm and moist air, and you move that warm and moist air over a cold surface, and you cool it, you chill it to dew point. And so, advection fog is so common, along the West Coast. Very, very common in San Francisco. There's a picture of the famous Golden Gate Bridge with advection fog. And, the nickname of San Francisco is Fog City, USA. But also Portland and Seattle. They're also, very, very foggy cities, too. Well, what's going on is you've got, the Pacific Ocean, and you've got the westerly winds. Now, advection fog is very prominent along the West Coast in summertime, much more so in summer than in wintertime, because that's when you've got warm water. And warm water is picked up by the westerly winds, warm air, with a lot of moisture in it, and you got warm, moist air. That's what you need, and then you move it over what? The cold California current. And so this warm, moist air moves over the cold California current along the west coast, and it gets chilled to dew point, and that advection fog just moves inland. It's not common in wintertime because the ocean is relatively cool, and cool, moist air moving over cool surface doesn't do anything. So you might get a little bit of fog, but it's really prominent when you've got warm, moist air moving over a cold surface. Now, there is a big difference between advection fog and radiation fog. Advection fog lasts. I mean, you can have persistent, warm, moist air moving over this surface, cold surface, all day long. So you can have fog that lasts all day long, or even days at a time. Whereas radiation fog usually evaporates by mid-morning, kind of burns off. Now, advection fog is also common in the northern United States in wintertime when you've got a snow-covered surface, right? And so what can happen is you can get a warm front, warm air moving up from the Gulf of Mexico, warm, moist air moving up from the Gulf of Mexico in wintertime, moving over the snow-covered surface, chill its dew point, and you get advection fog. And again, I mean, that advection fog over the snow-covered surface, you're just pumping in that Gulf air for days on end, and you can have advection fog for days, literally. So that ends this lecture number 1.